The dream of expanding human civilization beyond planet Earth and into outer space has captured our imaginations for over a century. With advances in rocketry and space technology in recent decades, we now stand at the cusp of making this dream a reality. Our first small step will be establishing a permanent human settlement on the Moon. With its proximity to Earth and abundance of resources like water ice, the Moon makes an ideal location for a first extraterrestrial human colony. The first lunar habitats will likely consist of inflatable modules covered in lunar regolith to protect residents from cosmic radiation, meteoroids, and extreme temperatures. These habitats can be expanded over time as more infrastructure is built on the surface. Solar panels will provide the initial power source until nuclear reactors can be set up to provide consistent energy. Using materials harvested on the Moon, colonists will start constructing permanent structures made of concrete or bricks. Underground lava tubes left over from ancient volcanic activity provide ready-made shelters that can be expanded and reinforced. As the colony grows over the years, larger domed structures can be constructed to house more people and provide agricultural spaces for growing plants. Breathable oxygen and drinking water will be extracted from lunar ice deposits. Communication antennas and satellites around the Moon will allow direct contact with Earth. After successfully establishing a long-term sustainable settlement on the Moon, Mars will be the next target for human expansion. Mars has an abundance of natural resources that can support human colonization efforts. Water ice exists at the polar ice caps as well as under the surface across the planet. This provides a source of drinking water and oxygen. Molecular nitrogen, argon, and carbon dioxide in the thin Martian atmosphere can also be converted into breathable air. Martian soil contains all essential elements like iron, silicon, aluminum, magnesium, sulfur, nitrogen, and calcium to grow food crops in enclosed habitats with adequate lighting. The planet also has significant deposits of useful metals like iron, gold, cobalt, copper, and nickel that can be mined and sent back to Earth. The first human outposts on Mars will likely be research stations staffed by rotating crews, similar to Antarctic research bases on Earth. These early colonies will allow us to better study the planet and determine ideal locations for larger-scale settlement. Flying unmanned robotic missions to Mars first can help identify hazards and valuable resources ahead of human arrival. As rocket propulsion technologies continue advancing, transit time from Earth to Mars will also reduce, allowing more frequent trips. Ships transporting colonists and cargo can take advantage of minimum energy routes that involve swinging by Venus or Earth's moon to adjust trajectories. This will reduce travel times down to just 3 to 4 months instead of 6 to 8 months. Faster trips mean less consumables required on board and lower exposure to deep space radiation. When selecting Mars colony landing sites, a key factor will be identifying locations with subsurface water ice. Not only can water ice be used directly for drinking, oxygen production, and irrigation, but the overlaying soil also protects human habitats from harsh surface radiation. Additionally, sites along the equator receive the most sunlight to generate solar power. Once landed, pressurized habitats will be inflated with equipment unloaded from landers. These temporary shelters can later be buried under mounds of soil or covered in concrete shells constructed as permanent habs. As the initial Mars colonies take root and expand, full-fledged cities can be built featuring enclosed biodomes, nature parks, manufacturing centers, and housing districts. Domed cricket farms and vertical hydroponic gardens will help feed residents while water recycling systems maximize resources. Colonists can enjoy parts of their new world while never needing to wear bulky spacesuits. Mars cities can even establish spaceports that open up the rest of the solar system to human expansion. Supporting such spread-out colonies across inhospitable worlds will require significantly lowering launch costs from Earth. A combination of reusable rockets, space elevators, mass drivers, and local resource utilization will make transportation affordable. Back in the Earth-Moon system, large space stations located at Lagrange points will serve as transport hubs for passengers and cargo heading Marsward. The Lagrange point stations will also support asteroid mining colonies. Asteroids contain precious metals, oxygen, water ice, and other useful construction materials not readily available on planetary surfaces. All resources extracted from asteroids will help fuel humanity's continued push deeper into space. The asteroid belt also contains a special type of asteroids called carbonaceous chondrites. Some theories postulate that life on Earth arose from microorganisms hitching a ride on such asteroids over 4 billion years ago. Studying carbonaceous chondrites up close could offer clues into life's origins. Beyond resource mining, asteroid colonies can participate in stellar hacking by constructing gigantic solar shades in space. By blocking a portion of sunlight, we can counteract some effects of climate change back on Earth. The asteroid colonies themselves will be warmed by mirrors reflecting sunlight or heat from solar thermal generators. After settling Mars, the next big milestone for human expansion will be establishing colonies around gas giants like Jupiter and Saturn. Instead of landing on actual planets, colonies around gas giants will be floating cities in the clouds. Colonies float in mid-atmospheric layers where temperatures and air pressure match Earth-like conditions. At this altitude, breathable air exists while protection from cosmic radiation is still provided by the upper atmosphere. Floating cities support agriculture, manufacturing, tourism, and research. These colonies access gas, liquid and solid resources available in the dense atmospheres of outer gas giants. Hydrogen, helium, methane and ammonia are abundant in the atmospheres and can be harvested. Colony airships float and propel themselves by adjusting the buoyancy of vacuum chambers. Some colonies feature massive solar panels harvesting abundant sunlight to power electrolysis plants that separate collected atmospheric gases. These atmospheric mining colonies require little infrastructure sent from Earth. Asteroids are tugged from the belt into orbits around gas giants. There, automated gas extraction plants separate out various resources before launching containers up to the cloud colonies. The helium-3 isotope is rare on Earth but occurs in abundance within the atmospheres of gas giants like Saturn. When fused with deuterium, helium-3 promises to deliver 10 times the energy output compared to traditional nuclear fusion between deuterium and tritium isotopes. Abundant clean energy will dramatically boost standards of living across human settlements throughout the solar system. Exporting helium-3 gas back to Earth provides a lucrative income stream to support more colonies around Saturn. Additionally, we can export hydrogen gas used as potent chemical rocket propellant. Mastering the fusion technology to utilize helium-3 could utterly transform human civilization. Fast interplanetary travel becomes possible while virtually limitless clean energy powers thriving colonies across gas giants. Next-generation fusion rockets would allow journeys to the far reaches of the solar system in months instead of years. While most known exoplanets are inhospitable gas giants, future's advancements in fusion rocket technology gives us the ability to set our sights on distant stars. At 10% the speed of light, the closest stars are just decades away. Our first interstellar colonies may be buried under the surfaces of icy moons around exoplanets. Once again we tap subsurface water for sustenance. With abundant energy, we can use solar or fusion power to create livable habitats under layers of ice. Here conditions exist to harbor diverse ecosystems that spring up around geothermal vents. Colonies inside icy exomoons tap geothermal heat to generate electricity and air conditioning. Chambers filled with plants nourished by grow lights provide beauty and greenery reminiscent of parks back on Earth. Larger enclosed caverns feature towering forests, streams, hills and waterfalls. Wildlife flourishes to support a thriving biosystem. Entire Earth ecosystems can be transplanted to give future generations a connection to the planet their ancestors came from. To grow these colonies exponentially, automated self-replicating constructor swarms build out additional structures and infrastructure using in-situ resources. Pulpy organics, rock, and ice feed raw material processors before automated construction arms assemble new domiciles. Colonists supervise while AI coordination expands colonies faster than if doing all manual work. By working in tandem with AI systems, humans spread throughout the cosmos. Even in a post-scarcity civilization freed from labor by advanced automation, humans still yearn to build, invent, create art, and explore. Our creative ambitions can never be satiated. Venturing into the galaxy lets us build monuments on epic scales rivaling celestial bodies themselves. Constructing megastructures like Dyson spheres and Matryoshka brains allows colonizing one star system, then harnessing all its energy output to propel growth across ever more distant stars. At this phase, spreading human consciousness itself across the stars becomes the goal rather than just biological human forms. Advanced neural interfaces allow minds to inhabit powerful robotic bodies built for the extremes of space. Beaming brain states via lasers enable fast travel between worlds and sharing experiences. Uploading minds into digital substrates gives extraordinary capabilities while retaining identity. Amassing knowledge from millions of immortal digitized colonists creates hyper-intelligent minds. The minds pilot nomadic interstellar seed ships which turn entire gas giants into massively parallel Matryoshka brains to calculate navigation solutions across the galaxy. Thus, human civilization grows exponentially without being hindered by the slow physical transport of frail human bodies across immense stellar distances. By pioneering each next frontier in turn, Mars then the outer solar system, then other stars, we grow humankind into a galactic civilization. Each small step builds technological capability and experience needed to attempt the next leap. Perfecting closed-loop resource recycling in Mars habitats allows creating autonomous seed colonies around distant stars. Mastering fusion rockets give us our first interstellar ships. And digitizing human minds provides immortal guides to spread our culture endlessly. The desire to expand and spread life burns strongly within us. Through advancing science we turn this drive into cosmic manifest destiny. We stand today at the start of this ascending journey pointed to the stars themselves. Our grandchildren may yet realize the dream of walking barefoot in the sands of distant habitable exoplanets and watching alien sunsets under strange new skies. The human urge to explore impels us inexorably outwards. Only by voyage can we discover who we were meant to become.